All right, look at this full room. Good afternoon, lads and ladies. Welcome to our last day of MAC 1140 pre-calculus. You have made it through all the way to the end. We are sprinting, we are huffing, we are puffing, we are wheezing, but the finish line is in sight. So, I have just one or two little things I want to show you guys today, some pretty cool shit. Tying in with where we left off last time. Now, other thing I need to tell you about, of course, is the take-home test, which is going out today. I finished writing it this morning. I'm going to publish it to Canvas immediately after class today. So let's get to it. I want to make sure everybody has a very clear picture of where we are and where we're going, because the next few days are critical. I don't know if you guys are here in Gainesville or not, but this morning when I woke up, it was frigid out. So much so I'm still in my long sleeves today, inside with the heat on. So announcements. I see there's some stuff in chat here. Right, yeah, so that's exactly what we're going to talk about right now. Exam 4 is a take-home. I'll show it to you right now. Ready? Now, you're not going to get it here. I'm going to publish it for you in Canvas. But here it is. That's the code. You don't need that. Over here is the test. All right. So this is exam 4. You see it's got questions, some of which say true, false, some of which have multiple choices, and the other ones are free response, yeah? There's some stuff to do with systems, some stuff to do with matrices, and some stuff to do with sequences, and some stuff to do with series. So let me walk you through it. The first and most important thing at this stage is that you read this shit. Read it, please read it, please, please, please read it. I'll read it here once. Read it again on your own. Carefully read and answer each question. For each true, false, multiple choice question, make certain that you clearly mark one and only one response. For each free response question, write out your entire solution showing all work, not just the answer. You can use your notes and your textbook. You cannot use anything else, including other people, okay? So I got no control over this. You guys are at home, you got textbooks. I'm not going to play. You can use your textbook. You can use your notes, but don't do anything else. I Google all these problems myself, and I look at all the top hits on Google. If I see anything that is suspiciously reminiscent of a Cora response or anything from Bartleby or anything from anywhere else, I will do my best to hang you up by your toenails. Don't talk to anybody else about these problems. Just solve them on your own using your notes and your textbook. That is fine. I would like it if you guys would print this PDF, which I will be posting on Canvas, and work on the page. But if you don't have access to a printer, that's okay. You can write out the problems. Just make sure you write the problems, the problem numbers, and your answers and full solutions for the free response problems. Then you will be uploading this, whether you print it and write directly on it, or whether you write on your own piece of paper, doesn't matter to me, but you will be scanning and uploading those solutions to Canvas. So over here in assignments, I'll do it right now even. Look here, exam 4. I can edit this so that y'all will be making a submission online by file uploads. And I'm not even going to restrict the file type. You can do it however you want. Okay, so when is it due? Let's talk about that. Where's your syllabus? You have from today, as soon as class ends, to the start of the final to submit this take-home test. All right, so your final is on the 7th. That's what, next Wednesday, right? Thursday? Really? Oh no, December 7th, Monday. All right. So these are the basics, right? Exam 4 is a take home. Read and follow the instructions. In the Canvas announcement. So what I'll do immediately after class, I will post a Canvas announcement with that PDF attached. You can save the PDF on your computer and then print it out or work on your own sheet, doesn't matter. Once done, scan your solutions. And answers and submit them to the assignment titled Exam 4 in Canvas. This is due at the start of the final, which we said was on the 7th at 3:30 p.m. Of course, you can submit it sooner if you want to, but you must submit it before the start of the final, no later than that. So is this all very, very clear? I'll post an announcement. That announcement will have the PDF of the exam. You save that PDF and either print it and work directly on it, or don't print it, but write your own answers on the paper, on some blank paper. Then you will scan your work and submit it to the assignment titled Exam 4 in Canvas no later than 3:30 p.m. on December 7th. Finals 3:30 to 5:30, 2 hours. All right, is that all nice and clear? Again, I would prefer if you print the exam. I would much prefer you print the exam and work on that paper directly. That'll make the scans a lot easier for me to grade. Final, I haven't written the final yet, probably around 20 questions. All right, let's tack this in here too. The final exam is 12/7/20 from 3:30 to 5:30 p.m. If you have any special testing accommodations or anything like that, for any reason you are not available during the scheduled time for the final, you need to reach out to me like today, because the college is actually very strict about when people are allowed to take final exams, even though it's a hybrid class. We have to play by the college rules or they get angry at me and I get in trouble. So if for whatever reason you have a conflict and you cannot take the final between 3:30 and 5:30 on the 7th, you need to let me know ASAP so we can figure it out. What else? I think that's all I got for you guys at the moment. So we can move on to the classwork if there is not any other kind of announcement-y type questions. Okay. So last time we were talking about sequences and series. Remember, a sequence is an ordered list of numbers. Like A1, A2, A3, and so on. It goes on and on and on forever. a series is a sum of numbers, like A1 plus A2 plus A3, and so on. We were looking specifically at a certain kind of series. Our last example was the series, I might call them capital S, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on, which can be written in the sigma notation as the sum n from 0 to infinity, 1/2 to the n. And I think I tried to convince you, we were fairly sure that S, this infinite series, was equal to 2. Because if we looked at the sequence of partial sums, S0 was 1, S1 was 1 plus 1/2, which was 1.5, S2 was 1 plus 1/2 plus 1/4, which was equal to, what is this, 1.75. S3 was 1 plus 1/2 plus 1/4 plus 1/8, which was like 1.93 something. Come on. Oh, damn it. I just cannot type today. Yeah, 1.875. These appear to be getting closer and closer to 2.
Can you go up really quick, please, so I can take a picture of the top?
Sure.
Thank you. Got it. Thank you.
Good. All right. So these things were called partial sums, right? This full series here goes on and on and on forever. And the best way we can wrap our heads around it is by asking, well, what happens if you let the sum get longer just one term at a time? So here's 1 term, 2 terms, 3 terms, 4 terms. If we keep going, those partial sums appeared to be getting closer and closer to 2. And we even had the formula for Sn, which I was able to graph for you and show you, yeah, it does get closer and closer to 2. So what I want to do today is come up with a more general formula. But before we can do that, I need to show you a few things about geometric series, in particular, geometric sequences and geometric series. So let's dive in. Recall that a sequence is called geometric if it can be written like an exponential. As an equals some constant, I call it a naught, times r to the n, where r is called the common ratio. Right, so this was a geometric sequence. We need to talk a little bit about what geometric sequences do as n gets bigger and bigger and bigger. So some examples we had were like 2 to the n. An equals 2 to the n. This is geometric. Here, a0 is 1, a1 is 2, a2 is 4, A3 is 8, and so on. If you look at the graph, A0 is 1, 1, 2, 3, 4, 1, 2, 3, 4. If you look at this graph, A1 is 2, A2 is 4, and this thing just gets bigger and bigger. The next dot is like all the way up here, right? And then the dot after that is off the page. So the graph of this geometric sequence is definitely not getting closer and closer and closer to any particular thing. It's just blowing up to infinity. If you look at the geometric sequence an equals 1/2 to the n, here A0 is again 1, A1 is 1/2, A2 is 1/4, A3 is 1/8. His graph we'll mark this as 1 up here. So this goes 1, 2, 3, 4, 5. Here I'll put 1 all the way at the very top here. A0 is 1. A1 is 1/2. A2 is 1/4. These dots are getting closer and closer and closer to something. They're getting closer and closer and closer to 0 as we go further and further and further along. Right? The graph of this sequence up here, he's just getting bigger and bigger. This sequence down here, they're getting smaller and smaller, and they're getting closer and closer and closer to 0. And this is hinting at that concept of a limit that we talked a little bit about last time. I want to look at one more example. What if I look at like -1/3 to the n? A0 again is 1. A1 is -1/3. A2 is +1/9. A3 is -1/27. This fellow's graph looks like this. A0 is 1. A1 is -1/3, so like right here. A2 is +1/9, which is like right here. A3 is -1/27. The next term would be so close to 0, I don't have room to write the number. This guy's also getting closer and closer to 0. So some geometric sequences go to 0 as n goes to infinity, but others go to infinity as n goes to infinity. And what we want to do is characterize which geometric sequences go to 0. So here's the theorem. The geometric sequence an equals a0 times r to the n will go to 0 as n goes to infinity if the absolute value of r is less than 1. And if the absolute value of r is greater than or equal to 1, then an will not go to 0 as n goes to infinity. So this is just a statement about the graphs, right? The dots on the graph will all get closer and closer and closer to the horizontal axis if the absolute value of the common ratio is less than 1. Like in this example we just looked at, the common ratio here is -1/3. And again, you see this behavior of the dots getting closer and closer and closer to the line y equals 0. others. Yeah, others was the other word here. So some geometric sequences go to 0 as n go to infinity, but others go to infinity as n goes to infinity. So now we're going to use this to figure out which geometric series the word is converge, which means have a finite sum, and which diverge, failing to have a finite sum. It turns out that there's a lot of subtlety in this. But in these particular cases where the things we're adding up are geometric sequences, those sort of series are relatively easy to work with. I can get an explicit formula for the nth partial sum, which is what I did for the series we were working with on Monday. I found an explicit formula for the nth partial sum of that geometric series, but I want to see how to do it in general. Where did my one?
Okay, wait, so to sum it up, when r is less than 1, the geometric sequence will go to 0, and then if r is greater than 1, then it won't.
Right, and it's not necessarily that r is less than 1, it's the absolute value of r.
Okay.
So like negative 1/3 has absolute value 1/3 is less than 1. So the sequence above did go to 0. But yeah, if r is not too far from 0, if r is within distance 1 of 0, then the sequence will go to 0.
Okay.
So let's keep this in our pocket and look at a geometric series. Geometric series are series built out of geometric sequences. I.e., series of the form S equals sigma n from 0 to infinity a naught times r to the n, which remember is shorthand for a naught plus a naught times r plus a naught times r squared plus a naught times r cubed, and so on. And you can factor the a naught out. So that's 1 plus r squared plus r cubed, and so on. This is the piece that we're really worried about. Just think about this for a minute. If r is equal to 1, then this series is 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 infinitely many times. You add 1 to itself infinitely many times, you're going to get infinity. But if these things get small, r squared, r cubed, if those things get small really fast, then adding infinitely many of them together may still give you something finite. And that's what we saw last time. If r is 1/2, then this series right here converges to 2, which is kind of mind-blowing. Now what I'm about to show you is why that's the case. Let's look at the partial sums Sn. That's A naught plus A naught times R plus A naught times R squared plus A naught times R cubed. But rather than going on and on forever, it has a second to last term, A naught times R to the n minus 1, and a last term, A naught times R to the n. So rather than being an infinite series, it's just a big but finite series. Factor out the A naught. Actually, you know, let's factor it out. And you get 1 plus R squared plus R cubed plus R to the n minus 1 plus R to the n. And now here's the magic. Multiply by 1 minus R. So we start by just writing out that partial sum. And then I'm going to multiply both sides of this expression by 1 minus R. So I get 1 minus R times Sn equals 1 minus R times A naught times 1 plus R squared plus R cubed plus R to the n minus 1 plus R to the n. You can shuffle the A naught over here, and then you just have 1 minus R times that thing, which I'll distribute. So that's 1 times 1 plus R squared plus R cubed plus R to the n minus 1 plus R to the n minus R times 1 plus R squared plus R cubed plus R to the n minus 1 plus R to the n. Now distribute the R and distribute the 1. And you get that 1 minus R times Sn is equal to A naught times 1 plus R squared plus R cubed plus R to the n minus 1 plus R to the n. There's me distributing the 1. This is this. Yeah, sneaky business, right? I chose to multiply both sides by 1 minus R. So I didn't get it from anywhere. It's just an idea. Let's try this, all right? Let's just see what happens if I multiply both sides by 1 minus R. Turns out something really nice happens. So here's what I get when I distribute the 1. It's this. And now when I distribute this minus R, I'll get minus R squared minus R cubed, right? R times 1 is R times R is R squared is R cubed, minus R to the 4, minus dot, 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 minus this would be R to the n, because it's R times R to the n minus 1. And then the last guy is minus R to the n plus 1. And now the fun is cancellation. Look at this. Here's a plus R, here's a minus R. Here's a plus R squared, here's a minus R squared. Here's a plus R cubed, here's a minus R cubed. There's a plus R to the 4 here that's going to be soaked up by this minus R to the 4. Plus R to the n minus 1 is going to be soaked up by the term right before this. Plus R to the n, he'll be soaked up by this. So the only things that survive, this is going to be A naught times this 1 and this R to the n plus 1. So 1 minus R times Sn is equal to this, which means Sn, my nth partial sum, is A naught times 1 minus R to the n plus 1 divided by 1 minus r. It's a sequence. It's a sequence of n, like the variable here is capital N, and this is a function where the input is capital N. This is a sequence. And this little piece of that sequence is geometric. So let's recap a little bit here. If that algebra feels like black magic to you, it's okay. It usually feels like that the first few times you see this. If you run through it on your own, you'll see it's really nothing crazy. It is just straight up regular algebra. But the decision to say, let's multiply both sides by 1 minus r and see what happens, that's a surprising thing. So somebody had to have a creative idea somewhere and say, let's do this and see what happens. And this is what happens. So I'm going to come back up here, and I'm just going to rewrite what we have. So the partial sums of this series is Sn equals a naught times 1 minus r to the n plus 1 divided by 1 minus r. Now, obviously, r is not allowed to be 1. If r is exactly equal to 1, this apparatus is undefined. If the absolute value of r is less than 1, then we know that r to the n goes to 0 as n goes to infinity. That's the theorem that we just stated a minute ago. So for absolute value of r less than 1, Sn, which is a naught times 1 minus r times r to the n over 1 minus r, because r times r to the n is r to the n plus 1. This guy will go to a naught times 1 minus r times 0 over 1 minus r, which is just a naught over 1 minus r, as cap n goes to infinity. In other words, an infinite geometric series will have a finite sum if the absolute value of the common ratio is less than 1. Now, for absolute value of r greater than or equal to 1, Sn just goes to infinity as n goes to infinity. Because this piece will just get big. So you get like 1 minus something huge over something normal. That's going to be something huge. The final result is this theorem. If S is a geometric series and the absolute value of r is less than 1, then S has a finite value. Namely, S is equal to a naught over 1 minus r. If the absolute value of r is bigger than 1, bigger than or equal to 1, then S does not have a finite value. And this is good stuff. Not necessarily between 0 and 1, but between -1 and 1. Yeah, the absolute value of r has to be less than 1, which means r itself has to be strictly between -1 and 1. -1/2 is okay. So we can use this to find the sum of the series S from last time, which was sigma n from 0 to infinity, 1/2 to the n. This is geometric. With a naught equal to 1 and r equal to 1/2. So the absolute value of r is the absolute value of 1/2 is 1/2, which is less than 1. So S is finite. And S is equal to a naught over 1 minus r, which is 1 over 1 minus 1/2. Just using our formula. But that's the same as 1 over, well, 1 minus 1/2 is 1/2, so it's 1 over 1/2, which is 2. And that's what we found last time by playing around, just calculating. But now we have a theorem that works. And this theorem can be used for all sorts of other cool shit. I know that your generation has long since moved on from Facebook. Facebook is the place where internet things go to die. But one of those stupid internet things that still, for whatever reason, has not died is that 0.999999 equals 1. I'm going to prove to you that that's actually true. Now, Brooks asked, what's the exponent of the third line down? Multiplied by 1 minus -1 negative r3 and the ellipses. So we're back here. So 1, 2, 3. The exponent here is n minus 1. So this is r to the n minus 1, and then r to the n. After this, this is r to the minus r to the 4, then minus r to the n, then minus r to the n plus 1. So this stuff is the result of distributing this negative r here. And this stuff is the result of distributing the 1 here. Okay. Yeah, so my next favorite thing to do with this is to show you what repeating decimals really mean. And this is actually a valid proof. Where do we want to go back to, Fabrice? Here? So if all of that algebra is driving you nuts, the important thing that we get out of that is this theorem. There's one thing you get clear in the notes, it's this. I'll hold here for just a second or two. All right, so moving on. This is true. This is true, but a valid proof of this is a little bit hard to find because repeating decimals like this, the only nice way, the only formal way to express them is as an infinite series. This is 0.9 plus 0.09 plus 0.009, and on and on and on like that forever. All right, if you add, for example, 0.9 plus 0.09, you get 0.99. If you add to that 0.009, you get 0.999. And if you keep going like that forever, you get 0.999999999, on and on forever. This is actually a geometric series. This is 9 times 0.1 plus 9 times 0.01 plus 9 times 0.001, and on like that forever. Zero 0.1 is 1/10. 0.01 is 1/100th, or 1/10 squared. 0.001 is 1/1000th, or 1/10 cubed. So the real way to prove this is to write it as a series. It's the sum from 1 to infinity of 9 times 1/10 to the n. Which is a geometric series. With common ratio r equal to 1/10. So the absolute value of r is the absolute value of 1/10, which is 1/10, which is less than 1. So the value of the series is finite. Comes from our formula. So 0.9999, on and on forever, follows that formula where we take the starting term, which in this case is 9 times 1/10, and we divide by 1 minus the common ratio. But that's 9/10 divided by 1 minus 1/10, which is also 9/10, which is 9/10 times 10/9, which is indeed 1. So this is how you actually prove that 0.99999 and so on is equal to 1. And you can extend this to lots and lots of other things, like 0.333333, 0. Anything repeating, any repeating decimal. You can play this same game with. It's cool stuff. I'm a fan. So what else is fun to do with geometric series? Oh, I don't want to break your hearts with anything crazy. So let me show you why we call these things geometric. I'll hold here for just a second. All right. So why are these called geometric series? Well, suppose I start with a square like this, and I'm going to go ahead and work with an explicit example because it'll be a little bit easier than working in the general case, but where this side length is 1 and this side length is 2. No, I'd be happy to do a homework problem after that. If I cut this thing in half, then the area here is 1 and the area here is 1. This is a 1 by 1 square. And if I cut that in half, then the area here is 1/2. This leftover piece also has area 1/2. If I cut that in half, then this has area 1/4. And this has area 1/4. If I cut that in half, then this has area 1/8. If I cut that in half, then this has area 1/16. So the total area is this area plus this area plus this area plus this area plus this area, and on and on and on like that forever. But of course, just using geometry, the total area has to be 2 times 1. So there's another way to get that result, that 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 and so on forever and ever has to be equal to 2. And you can do this with any geometric series. You just chop it up into thirds and then chop each third into thirds and then each third of that into thirds. And you add them all up and you get the same sort of thing. So this is why we call these series geometric, because you can actually compute them using geometry. And there are connections here to things like golden spirals and stuff that you've maybe seen in popular mathematics, or movies or something like that. But it's cute. It's cute. And that, ladies and gentlemen, is the end of MAC 1140. This is the end of what I require you to know to move on into calculus. There are some things that I would have liked to have talked about this semester that we haven't had time to. Yeah, big celebration, right? It is good stuff. Topics that you may want to look into. Topics we didn't get enough time with. Some people would say conic sections are important, but they're not. But partial fractions. This is important. Patrick JMT has really good stuff on this. You won't need it in Calc 1, but you will need it in Calc 2. Really, that's it. That's it. You could toss conic sections in here if you wanted, but conics aren't important anywhere in calculus. But if I had an extra week, I would love to tell you guys a little bit about partial fractions. It fits in really nice at the end of our discussion on matrices. But we just don't have time for it, and it's not something you'll need for Calc 1. You will need it for Calc 2. Every Calc 2 professor goes over it from scratch as though you've never seen it before, but it's much, much easier if you do read about it beforehand. So it is in your textbook. It's in the end of chapter 12 there after talking about matrices. You can get it all just by watching 1 or 2 Patrick JMT videos. I teach all the math classes at Santa Fe. I don't think I'm doing any trig in the spring. I think in the spring I have a few Calc 1s, Calc 2, and a couple college algebras. But if you're looking for recommendations who to take your next class with, you can always reach out to me. I'd be happy to help with that. But we've got a little bit of time left here, and I think there are some homework problems that that 1 or 2 people wanted to see. So no, I don't think, Brooks, I don't think I'm doing any trig in the spring, but I can recommend some people for trig if you're looking. If Adam Christofferson is doing one, he's very good. If Aaron DeGon, Brandy Cook, or Sarah George are doing any trig, they're also very good. I would caution around a few people, Joe Mosul and Larisha O'Reilly. They're both wonderful human beings. I love them as people. But when I've seen students take trig with them and then move into calc, they're just a little too soft. So people end up with not quite as strong skills as they need. Karen, yeah, Karen Milner is very good. Yep. Okay, so Lily wants to see number 33. Is that from the study guide, the most recent homework set? Okay. Let's take a peek at that. Oh yeah, good stuff. So you do want to get comfy with this summation notation. There's stuff like this on the test. Here we want to find the sum from I equals 1 to 5 of I times 2 to the I. So the trick here is just getting comfortable writing these out and understanding what they're saying. All right. So remember what this means. This symbol here, this sigma, says take this thing and add it up over this range of the variable I. So when I is equal to 1, we get 1 times 2 to the 1. Plus, when I is equal to 2, we get 2 times 2 to the 2. Plus, when I is equal to 3, we get 3 times 2 to the 3. And then 4 times 2 to the 4, and then 5 times 2 to the 5. So this is the kind of critical step here, is just going from this to this. And now because this is finite in length, we can compute this. 1 times 2 to the 1, that's just 2. 2 times 2 squared is 2 times 4 is 8. 3 times 2 cubed is 3 times 8 is 24. 4 times 2 to the 4 is 4 times 16 is 64. And 5 times 2 to the 5 is 5 times 32 is 160. And then we just add these bad boys up. So 2 plus 8 is 10. 10 plus 24 is 34. So I'll help myself out here. These first guys are 34. So you have 34 plus 64 plus 160. 34 and 64 is 98, right? So that's 98 plus 160. And then 100 plus 160 would be 260. This is 2 smaller than that. So this is 2 smaller than 260 is 158. Or sorry, 258. So again, I think the critical thing is just starting out like this. Okay. Alrighty, guys, we got about 15 minutes left and we can spend it doing whatever you would like to do. So from all the stuff that we've talked about, especially the stuff coming up on the test, even though it's a take home or it could come from anywhere in the semester, what would you guys like to work on? I've got about 15 minutes, probably enough for about 2 or 3 problems. Or if you don't have anything you want to see, I do have one other cool thing to share with you if you'd like. About 20 questions on the final. Yeah, expect about 20 questions. And the final will be formatted the same way all the other midterms were. They'll be in Canvas. You'll have to use HonorLock. Quick note about HonorLock. HonorLock pushed an update. I don't know if you guys have seen or heard about this, but HonorLock is releasing a new version. I don't know why they chose to do that at this time of the year, but you may want to uninstall and reinstall the HonorLock extension in your Chrome browser. I've heard some people complaining that they tried to access their tests, didn't work because HonorLock hadn't updated. It's supposed to update automatically, but it doesn't for everybody. So you may want to, sometime between now and the final, manually uninstall the HonorLock extension and reinstall it to make sure you update to the latest version. But yeah, about 20 questions on the final. All right, what else is on our mind? Anything else we'd like to look at here? if you don't have another question for me, I have something cool I'd like to show you. And I'd like to go back to when we talked about polynomials. Remember, we talked about finding roots. So if I wanted to find roots of the polynomial p of x equals x cubed minus 1, we can actually factor this as x minus 1 times x squared, what is it, plus x plus 1. And this guy has the single real root, x equals 1. This guy has two complex roots. You can get them out of the quadratic formula. They are the square root of 3 over 2 plus and minus I times 1/2. Is it that? Is it? Negative root 3 over 2 plus and minus I times 1/2. Now, this is not something that we've talked about in this class, but complex numbers you may have seen in the past can be plotted on a real axis and imaginary axis. If I plot the real number 1 over here, then I can plot the other two numbers, minus root 3 over 2, 1/2, here and here. These guys, it turns out, form an equilateral triangle in the complex plane, which is what this is called. If you study the roots of equations like these, x to the n minus 1, it turns out they always form what's called a regular n-gon. So if this was like x to the 5 minus 1, you would get a regular pentagon. If this was x to the 6 minus 1, you would get a regular hexagon. If there's one thing I would like to show you to try and convince you that algebra is way more beautiful than anybody ever told you in the past, it would be this. So let this be my little parting message to you guys. If I take random polynomials with degree less than 5 and integer coefficients running from -4 to 4, so you take all possible polynomials of degree 5, where the coefficients, the numbers in front of the x's, are whole numbers going from -4 to 4, and I plot their roots in the complex plane, it looks like this. In here, you'll see the equilateral triangle I just showed you. Here's the 1. Here's negative root 3 over 2 plus 1/2 I, negative root 3 over 2 minus 1/2 I. And you see right here that equilateral triangle. You can see the square you would get from x to the 4 minus 1 here. You can see the hexagon you would get from x to the 6 minus 1. It's boom, 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 boom. The geometry and the symmetries here are really beautiful. If you allow yourself to play with a little bit more, so now we're looking at all polynomials of degree less than or equal to 24, with coefficients still running from integers -4 to 4, you get this picture. And where's the large version of it? I'd like to show you this large version before we leave. Which you can get here. Adam Christofferson is very good. I think I do have a non-honors section of Calc 1, but it might be full. Adam Christofferson, if he has a non-honors section that is open, I fully recommend him. He's very, very good. All right. So here's what you get if you take all the polynomials degree less than 24 with whole number coefficients running from like -4 to 4, and you plot all their roots in the complex plane. Just like those 3 that I drew for you a minute ago. The shapes here are really amazing. You start to see what look like a lot of familiar fractals, if you've ever studied fractal geometry at all, around the edges here. These are called dragon fractals, and they're not defined to be this thing. The fact that these show up here at a glance looks like a coincidence. Also amazing is that they want to stay away from points like I and 1 and -1. There's very few around here. There's just one right in the middle. And if you zoom in on any of these sort of interesting looking, he won't let me in there. Let's see, my browser is shitting itself because this file is nuts. I think there are some shapes in here that are similar to the Koch snowflake, but they're not coming from the normal definition. So what's interesting about this is that you see all of these really familiar fractal shapes, feather fractals, coming from a place where you really shouldn't be getting them, as roots of polynomials. The symmetries here are amazing. This picture exhibits like a folding symmetry from both dimensions. It also exhibits a lot of rotational symmetry. The people who study these sorts of objects in general, this is why mathematicians care about polynomials, is because there's actually a lot of really fascinating symmetries. And by studying polynomials, you can discover some shocking symmetries that have extensions and applications well outside of mathematics. For example, dynamic systems and queuing theory, figuring out the fastest way to get people onto and off of an airplane, or the fastest way to get people who need treatment in an emergency room to the right kind of doctor, all follows from studying dynamical systems, which are intimately connected to fractals. And the shock here is that fractals are intimately connected to algebra and roots of polynomials. I remember seeing this sometime around pre-calculus, and it utterly blew my mind. So I just wanted to share that with you in parting before we leave here. There have been a few really good write-ups on it. You can read in your own time if you want to. Or if you wanted to, you could come to the math club, which hopefully will start doing in-person meetings again soon. Yeah, this is neat. Some of these close-ups appear some of the drawing fractal. But we're not doing them right now. So hopefully we'll have in-person meetings with the math team again soon. And if you wanted to look into anything like that or any other weird topics in math that you've just seen or heard about or thought could be cool, I would be happy to do that with you, and we can investigate whatever math topics you want: symmetries, algebra, calculus, fractals, whatever. Yeah, that's sweet. I appreciate the sentiment. I do have to get running. I've got a few other things to do today. So if there aren't any other questions related to class, then I'm going to go ahead and call it here. Are there any other homework problems or study guide problems that you guys would like to take a look at before we go? I'm really glad you enjoyed the semester. Yeah, I'm again, very proud of you guys for hanging in here. You've done a good job. So continue working hard. Don't let this bizarre online bullshit get you down. If you continue working hard, then everything will come back together just how we all hope it will at the end of this COVID madness. If you're taking a class with me next semester, I'll see you next semester. Otherwise, feel free to reach out anytime you have any questions. Of course, especially before the final. All right, I hope you guys all have a beautiful holiday. Good luck on the final. Remember to download and hand in that take-home test before the final. So I'm going to go ahead and publish that right now. I recommend working on it right away. Print it if you can, please, and then scan and upload your solutions. Make sure they're legible no later than 3:30 on the 7th.
Wait, I have a question,
yeah,
Professor.
Sure.
For the study guide 4, I couldn't answer some questions because I didn't know how to do them. And like it was due today at 2 p.m. Is there any way that you can extend that or no?
Yeah, of course. Yeah. Just go ahead and submit an extension request. I'll come in here and clear these out as soon as I finish.
Okay, perfect. I'll do that now.
All right, cool.
Thank you so much.
Of course. Yep. Take care.
Bye. See you next semester.
Sounds good. Bye, guys.